Welcome to the session on practical quantum techniques. I'm Joanna Freixanet. I'm part of the quantum algorithm engineering team. And today I'm going to talk about how to implement quantum algorithms in near-term quantum hardware. So we're going to see, first of all, of motivation on which algorithms it's interesting to implement. Then we're going to see the different steps that one needs to take into account to implement those algorithms and which techniques or tools can be helpful to do this. And then we're going to see in particular the step of execution on noisy quantum hardware. So we're going to check error mitigation and error suppression techniques that can really help us get the better out of quantum devices that are available right now. Okay, so we're going to start by motivating why it's important to scale quantum algorithms. And I wanted to start with the idea that quantum computing is not just a faster or better version of classical computing. We all know that there's problems that can be easy for classical computers, meaning that the resources that we need scale polynomially with the system size, for example, doing arithmetic operations. And then we have problems that scale exponentially or combinatorially with classical computing, and therefore they're hard problems for classical computers. An example here is the factorization of prime numbers. Then we know that, for example, with factorizing prime numbers, quantum computers have it easier. And in this case, we know an algorithm, the Shor's algorithm, that can do this with an exponential speed up. This is not the only case. Then there's a bunch of problems that we think could be better approached by quantum computers. For example, the idea is that simulating quantum mechanics should be easier, even though it's not proved by using quantum computers. In general, we want to move beyond things that classical computers can do well and start approaching problems with quantum computers that are better done with quantum computers to, at some point, observe an advantage. In order to do this, what we need to do is to start scaling our workloads for quantum computers, because if we work at a system of 20 qubits or less, we have something that can be simulated with brute force classical techniques, and therefore this is not going to bring anything new to the picture. For example, IBM quantum systems, all of them already have more than 100 qubits. So moving towards that regime allows us to know at least that by brute force classical techniques, we cannot reproduce what we're doing with the quantum systems. In certain cases, approximate classical techniques, such as tensor networks, for example, can be very, very good at solving those problems, and therefore we're not talking about problems that cannot be approached at all with classical computing. But we see that this happens for some specific systems only, and as we increase the number of qubits more and more, at some point we're going to reach domains that are much well dominated with quantum computing. Here is an example of all of this. In 2023, in the so-called utility paper, they published some results of that could be obtained with a quantum computer. And these were results that cannot be computed with brute force classical techniques. Then we saw many other results in the literature using approximate classical techniques, such as tensor networks mostly, that allow us to get close to the results from the quantum computer. We see that all of these techniques, including the results from the quantum computer, they do not agree exactly on each other. So this means that we're studying something in a regime that it's already very, very hard for classical computing. It's also hard for quantum so far. Like we really needed to find a problem that can be solved, and we're getting better and better at it. But we can see already here that we're in so-called utility regime in which both classical and quantum techniques are struggling. And as quantum devices get better and better, they're going to surpass what can be done with classical computing. So in order to start seeing interesting use cases that can be approached with quantum computer, we need to do two things. On one hand, we need advancements in different algorithms. And in this Qiskit Global Summer School, there's been already some sessions in which you saw different quantum algorithms and how we should be thinking about them nowadays. Hopefully, by doing advancements in algorithms, we're going to see that some of the application use cases, are going to come closer to circuit widths and circuit sizes, so number of gates and qubits that can be executed with with near-term quantum hardware. On the other hand, we need to advance quantum hardware and software in order to enable new applications. In this talk in particular, we're going to focus on this. We're going to focus on how to use software for the near-term quantum hardware that we have available right now to better approach some of the techniques, some of the algorithms that we want to implement. So we're going to be focusing on this, on how to run quantum algorithms on quantum hardware. For this, you have available something called Qiskit patterns and Qiskit add-ons. These are two different things. And this allows us to have a collection of tools and items that we can use when we're trying to implement an algorithm. These tools are based in different steps. These are the steps that one needs to follow when implementing any kind of quantum algorithm. So we need by start with mapping our problem into a quantum circuit and a set of observables. So something we're going to execute and something we're going to measure. Then we need to optimize this circuit for quantum execution, meaning that we need to make this circuit ready. We need to transpile it into the hardware so that it can be run. Then we need to perform the actual execution, and this means running the circuit and getting out some outputs, could be expectation values or samples. And finally, we need to post-process these outputs of the quantum circuit and obtain whatever we want to obtain, a plot that we want to show, or some results, or even the post-processing can be more involved in certain cases. For each of these steps, we have different tools that Qiskit gives access to. So, for example, we have the Qiskit circuit library to map our problem into different types of circuits, and this already gives us ready, prepared circuits that can help in certain cases. In other cases, we'll have to build them ourselves, but we have also access to the gates. For transpilation, we have the transpiler. For execution, we have the primitives, the sampler and the estimator, that are the kind of outputs that we want to get. And here we also need to specify which kind of error suppression and error mitigation we want to take into account. And these are things that I'm going to be focusing on later. And finally, we need post-processing, and for this we have the quantum info and quantum visualization packages of Qiskit that allow us to do that. On top of all these tools given by Qiskit, nowadays we also have access to the Qiskit add-ons. These are techniques that are a bit more involved and work only for certain types of problems, but this will allow us to for example, get better depths or run things that otherwise we could not run if we didn't take into account these more advanced techniques. So, for example, for the step of mapping, we have the Qiskit circuit library that gives access to a set of operations and a set of gates that we can use to build our own quantum circuits to do whatever we want to do in our algorithms. For example, imagine that we want to implement time evolution of a certain quantum system. We want to see its dynamics as time evolves. Then we would like to implement a Trotter circuit, most probably. So we can take different types of gates, or we can also take from the circuit library the evolution of a certain Hamiltonian, and then we end up with something that could look like this with different layers of Trotter steps. This is what the Qiskit circuit library allows us to do. But then in this mapping stage, we have two Qiskit add-ons that allow us to reduce the depth of this circuit by considering more advanced techniques. So, for example, multi-product formulas, what they do is to say, okay, so you have your Trotter circuit with with a number of Trotter steps. You need this number of Trotter steps to be accurate and have a small error in this approximation of the evolution you're doing. But this might be too deep. So in order to try to decrease the depth of this circuit, what we can do is to run product formulas, so like combinations of these Trotter steps with less steps. So here we have 1, 2, or 3. And then take a linear combination of these product formulas to reproduce the total evolution, the total set of Trotter steps that we were trying to implement at the beginning. In order to implement this algorithm, one needs to compute these coefficients of this linear combination, and this is done by solving a linear system of equations, but there's different heuristics that need to be chosen. So, for example, what numbers of Trotter steps, so these 1, 3, 2, and 3 that we're choosing here, are we gonna take, and what is the time that we want to time evolve this system. There's another Qiskit add-on that can also be used for this mapping stage. This would be the AQC tensor. And this is also about reducing the depth of our circuit. But here we're going to be doing it a bit differently. So the idea here is to take the first part of the circuit. This is some time evolution up to certain time. And then let's take it up to a time that can still be computed classically using tensor network algorithms. For example, TEBT. This is a tensor network algorithm to perform time evolution. So you can perform this classically, get the state that you would have with this time evolution, and then you would get it as an MPS, and then you can use approximate quantum compiling to map this state into a circuit using less gates than what you would use to do the time evolution with a Trotter circuit. And then you have this first stage already prepared, you reduce the depth of this first stage, and then you continue the evolution from then on. So in this way, you end up with a depth that is smaller. And you've also been using a combination of classical and quantum techniques in order to do this. All these Qiskit add-ons, you can find their documentation online, and they're ready to be implemented. And also you can have access to the GitHub and the code that implements them. So this makes them very useful. Then, for example, on the optimization step, when we want to transpile our quantum circuits into the quantum hardware, we also have Qiskit gives us the fast manager, which allows us to do all the different sub-steps that need to be done in this procedure. For example, we need to start taking our circuit, validate that it translates to the gates that need to be implemented, which would be like single qubit and 2 qubit gates, and then choose a layout for each of the qubits to go into a qubit of the device. In this case, we have qubit 0 and qubit 1, and we're mapping them to qubit 57 and qubit 58 in this device here. The next step would be if these 2 qubits, for example, are not connected. In this case, they are, but if they are not, we would need to introduce some swap gates in order to connect them, in order to implement the 2 qubit gates that are defined in the circuit. Once this is done, we also need to translate the gates here into gates that are native of the device that we're using. And we can optimize the whole thing in order to get better and better approximations of this ISA circuit so that the depth doesn't increase so much. And finally, the scheduling part of it is like really thinking how all this will be implemented in the device. So this transpilation requires a lot of different steps, but in principle, Qiskit does this for you, so you don't have to worry. You just have to set an optimization level, and this optimization level will try to get, with more or less effort, the best mapping and the best transpilation of the circuit into the device. Apart from the transpiler, again, we have different circuit add-ons that allow us to change the circuit at this stage for specific purposes that we might want to have. So, for example, we have circuit cutting. For circuit cutting, sometimes imagine that you have a circuit that is too long and you want to cut some wires, or you want to cut some 2 qubit gates because the circuit takes too many qubits. This can be done, but at the expense of doing more executions of the circuit. So then when you make these cuts of wires or qubits, what you do is that you end up with smaller circuits. These smaller circuits, for some reason or another, are better executed on hardware, and that's why you're implementing this technique. And then from the output of these smaller circuits, you then reconstruct the output of the bigger circuit. As I said, in order to do this reconstruction, this has some overhead in terms of number of executions, and in fact the overhead is usually not very good, so it increases exponentially, and usually the order of 3-4 cuts in a circuit is already a lot. So it's not like we can just take a huge circuit and cut it and then we would get the results for free. We need to have some trade-offs, but in some cases this might be able to help. We also have operator backpropagation for the second optimization step. And this is a similar idea of like, if we have circuits that are too deep, we might want to reduce the depth by, in this case, absorbing the end part of the circuit into the observable. So this works only in cases in which we're trying to compute expectation values. Imagine that you have a circuit, that would be the whole circuit here at the top part of the slide, and we perform some measurement. Instead, you could take this last part of the circuit, the unitary C, and then put it together with the observable. and trade off some depth of the circuit for a number of observables. Because when you're absorbing this into the original observable, you end up with some new observable that will have more Pauli strings, so it's a more complex observable. This is more difficult to measure, but we've reduced the size of the circuit. This doesn't come for free then, but in some cases in which this last part is Clifford or almost Clifford, the overhead is not very big. For the execution part, here we want to use the primitives to get an output of the circuit, and the primitives are the sampler or the estimator. For example, the sampler allows us to obtain the probabilities of each basis state by measuring the output of the circuit several number of times. This number of times is set by the number of shots, and then we can obtain some histogram like the one you can see in the screen that tell us what is the state that we were measuring. This is interesting for some particular algorithms that you might want to implement this, or in some cases you might want to implement the sampler and then from this information reconstruct expectation values of different operators. But if you just want to reconstruct the expectation value of an operator and you don't want to bother on how this is done, then one would use the primitive called estimator. This is exactly what it does. And in the under the hood, what we do with the estimator is still use the sampler, but do the changes of basis that are needed and then computing expectation values. So what I mean here is, for example, if you have a quantum state, there is the superposition of 0 and 1, and you have some observable, that is the x observable. If you would like to get the expectation value of this observable on this state, we would need to prepare the state, then rotate the basis, because we always measure in the z basis, and then get a set of measurements. With this set of measurements, we reproduce or we get a histogram, and then the mean value of this histogram is going to be the expectation value of the observable. For more complex observables, this becomes more difficult and it can be made more or less efficient by implementing things like grouping and so on. But the estimator in principle would do this for you. We'll see that some error mitigation techniques later only apply to the estimator, so they only apply to expectation values. And in Qiskit, they're only implemented for this, while the sampler, even though that it gives us more information, in some cases cannot benefit from some of these techniques. So these error suppression, error mitigation techniques that I was just mentioning, we'll see them in more detail at the second part of the talk. But the idea here is that we know that we don't have error correction yet, so we have to deal with the fact of having some noise, but we can still try to recover a better signal by using some post-processing in some cases, or in some cases by changing a bit the circuits that we have available so that we suppress some of the noise of the signal. As I said, we're going to see this in detail later. But the primitives, both the sampler and the estimator, allow us to implement them very, very easily. Finally, we have the post-processing stage. This would be, in some cases, just visualizing the results of the circuit, and you can see here a histogram. In some other cases, it can be something more involved, but this is really problem dependent, so I'm not going to enter into detail. Just to say, though, that here we also have some Qiskit add-ons that can help us. One of them is a error mitigation technique that is implemented as a Qiskit add-on. We're later going to see the ones that are implemented with Qiskit. One of them is matrix-free measurement mitigation. This Qiskit add-on is some error mitigation technique that, in contrast with the other ones that are implemented in Qiskit, is implemented in some add-on, and it works by considering which would be the ideal distribution that you're expecting to observe from a quantum circuit. And since usually the state that we have is just exists or has a support in a small region of Hilbert space, then it's easier to correct than just inverting the whole matrix. Another example of a Qiskit add-on that works for post-processing is the SQD algorithm, the sample-based quantum diagonalization. You're going to see this algorithm in more detail in one of the other sessions, but basically the idea here is that we're using the quantum computer to prepare some state and sample from it. And then we're using a classical computer to use these samples, which are sets of bit strings, to project the Hamiltonian onto these sets of samples, and then perform some classical diagonalization of this projected Hamiltonian, which is going to be smaller than the initial Hamiltonian that we had. By doing this, and we can leverage both quantum and classical computing and then obtain ground state energies of molecules, for example. So this is a very interesting algorithm, and it uses this part of the SQD is considered in the post-processing stage because we really use quantum computer for the first part of the algorithm, and the second part is performed, this case, on an HPC or in a classical computer. As I said, all of these add-ons are available. You have access to the GitHub, different documentation, and to the code. So if you're interested in implementing them, you could do it. So now we're going to be focusing. We've seen all these steps with the Qiskit add-ons and also the Qiskit patterns and the different tools that are available. We're going to be focusing on one specific thing, which I believe is the most important, and in some cases it becomes the difference between being able to execute something and getting reliable results and not getting them, which is the fact that we're executing on noisy quantum hardware. So we have noise in our devices, and we have different types of noise. Let's see what type of noise we have and how we can approach them. On one hand, we have environmental noise. So this environmental noise is most important for circuits that are deep, so that have many, many layers, and sparse. So in this way, some of the qubits are idle for long periods of time, meaning that they're not used, but we should conserve the information on them because they've been already initialized. This environmental noise can come from different things. It can come from a bad system coupling of these qubits coupling to the environment. It can come from crosstalk, so qubits talking to their neighbors. This happens. It happens less in new Heron devices, but it's something that it's good to take into account. And we have also decoherence. We know that in these quantum systems, information is lost over time. And if one looks at the devices in the quantum cloud or the quantum platform, we have the different characteristics for each device, and this median T1 and T2 can give you the decoherence times of the qubits. On the other hand, we also have readout errors. Readout errors happen because when we measure, we're doing imperfect measurements. So sometimes we might have a qubit that is in state 1, and we measure 0 or the opposite. This is most important for shallow circuits because the other types of errors, such as environmental errors or other errors that we're going to see in the next slide, are not so important, and therefore measurement errors have a very, very important impact. This can be seen also when one looks at the characteristics of a given device as the median readout error. And this gives you an error per qubit. So if you look at the qubits here, you see that they're lighted with different colors depending on which error is associated to them. Some of them have a readout assignment error that is larger, so maybe it's good not to use them when we try to implement the quantum algorithm in this device. We would try to avoid this qubit here. In particular, readout errors usually come in what we call SPAM errors. These are state preparation and measurement errors. And it's the error that you would get when preparing, for example, a state 1, and then you measure 0 instead of 1, and so on. This kind of concept is used for calibration of devices, and it takes into account this kind of errors. Then we have gate errors. Gate errors happen because when we operate on qubits, these operations are imperfect, and they're more important for deep circuits that are dense, so when we have a lot of gates, as the region that you can see here. Also, when looking at the characteristics of a device, you can see what are the median errors for certain gates. So, for example, here you would have it for single qubits, so single qubit gates as the SX, and 2 qubit gates as the CZ. An important thing to take into account here is that errors for 2 qubit gates are always much larger, so 1 order of magnitude larger than errors for single qubit gates. So all the error mitigation and error suppression techniques that you're going to see later are going to mostly be implemented on the 2 qubit gates because these are the ones that we're really worried about. Also, when we talk about the problematic depth of a certain circuit because it has too many gates and therefore noise increases too much, we're talking about gate errors. And in particular, we're worried about 2 qubit layers of gates. So we know that we don't have error correction available yet. Error correction will the idea would be to build up on redundancies that allow us to detect errors when they occur. So then we would be working with logical qubits that are essentially or almost error-free. Before that, we have to use other types of techniques to approach or to deal with noise. And this would be error suppression and error mitigation techniques. This differentiation is made because the techniques are slightly different. So in the case of error suppression, what we want to do is to minimize the impact of noise by either preventing errors from happening, so changing the circuit so that some errors are just cancelled or they don't happen, or modifying the circuit so that the type of noise that it's happening there is a bit different and maybe it's a bit more well behaved. This would be dynamical decoupling and Pauli twirling. For error mitigation techniques, we do something a bit different. So we allow errors to occur. So we're not changing the circuit to avoid them, but we're still having them. But then we reduce their effect by learning something about these errors when we're executing, and then kind of compensating for them. This would be twirl without extinction and zero noise extrapolation, some two other techniques that I will explain. We also would see here PEC that I'll briefly mention at the end of this part. So for error suppression, as I said, we need to change the circuits before. And for error mitigation, we change the circuits. So we apply some post-processing after. And sometimes, and most of the times, we have some additional quantum resources that dominate. So we might have to do more executions, for example, to learn the error or to change, to model something in order to cancel it later. Just let me give you an example of one of these error suppression techniques that is very simple to see. One of the types of errors that I mentioned before is crosstalk. For crosstalk, we have this problem that the qubits interact with their neighbors because the qubits are idle. So because these qubits are not being used, we can just keep these qubits busy and then this crosstalk will disappear. This is exactly what's done with dynamical decoupling. We just implement some single qubit gates. As we've seen before, single qubit gates have error rates that are one order of magnitude slow, like less than 2 qubit gates. So they're not so problematic. If we insert gates that end up summing to the identity, so they cancel each other, we're not doing anything on the qubit, but we're just keeping it busy. We can do this with X gates, but we can also do this with other sequences of gates. And we don't need to implement it in qubits that haven't been initialized, because here we don't have any information that we want to preserve. Let's see how we would implement this dynamical decoupling. So in general, let's say we want to run something on a quantum device. We first need to define the Qiskit runtime service and choose a backend. In this case, we're just choosing the backend that it's least busy. Then what we're going to be doing here is we're going to be using sampler options and estimator options to tweak all the different characteristics of error mitigation and error suppression techniques that we want to use. This is, I would say, more advisable than using resilience level. So the resilience level, what it does when we set it with the estimator, it activates some error mitigation techniques or others. You can set it to 1 or to 2. This is something that you can find in the documentation. Instead here, I'm just going to set it to 0. So I'm going to disable all the error mitigation techniques, and we're going to activate them slowly. And with each of them, I'm going to show you which are the different things that you can tune. And then you run the sampler or the estimator, whatever you want to use to get an output of your circuit. So we're going to define it and then you would run it. So let's imagine that we have this set already. And here I define the options, whatever I want to use. And we want to configure dynamical decoupling. So then we would use options, dynamical decoupling, enable true. This enables it. Then we define which sequence type we want to use. So if we use the XX sequence, we're doing what I showed you before. So going back here, we would see the sequences of X's. If we use other sequences, then we just have other gates that are keeping the qubits busy, let's say. Then we have Extras-like distribution. This is how these sequences are distributed in time. And the scheduling method is the same. So if we want to set them as soon as possible or as late as possible when this actually happens on the quantum hardware. This I would usually keep it default, and I would change the sequence type. Maybe the most complete one that allows that fights best crosstalk is XP X-. Dynamical decoupling, as I said, maybe is not so important for Heron devices, but for Eagle devices, really makes a difference. This is for dynamical decoupling, but for all the other types of errors, we have other techniques that can help us. So we have that the other error suppression technique, Pauli twirling, works for gate errors, and then the two error mitigation techniques, CNE and T-Rex, would tackle gate errors and readout errors. So now let's see some of the techniques that are based on manipulating noise, and then this is helpful for characterizing it. This would be Pauli twirling and the noise learner. As we've seen, Pauli twirling is an error suppression technique in a way because it modifies the noise of our devices, and the noise learner is something a bit different, but it's a way of learning how our devices work. Here, just to mention, it's important always, and I'm not going to dive into this in this session because there's other sessions that are going to be specialized on this, but relying on benchmarking and calibration of the devices is always going to be helpful to get good results. So let's start with Pauli twirling. Pauli twirling, the goal of it is to go from an arbitrary noise channel that we don't know exactly how it's acting on our states to Pauli noise. Pauli noise is better behaved because it accumulates linearly in contrast of, for example, coherent noise. And then it's, in some cases, it's also easier to mitigate. So we'll see that zero noise extrapolation, for example, is better when we know that we have Pauli noise. We see that both the noise learner and other techniques assume that the noise of our system is Pauli and so on. So we want to usually implement Pauli twirling. I would say it's a technique that it's advisable to implement it and it doesn't have much of an overhead. So if we have a noise channel, we're going to call it lambda, and we want to transform it into some Pauli noise channel. What we can do is to sandwich this noise channel into like Pauli operations. So for example, X, Y, or Z operations. If we do this with the noise and then we randomize over all these possible combinations with equal probability, what we would see is that we end up with some channel that is a Pauli noise channel. So let's say that instead of running this is not a circuit yet, this is just a noise channel, but doing it as a number of times with the same channel, we just randomize over these times and we sample from this. Now we want to apply this, but instead of doing it onto a noise channel, we want to apply it on a gate. So imagine that we have a gate, and we know that gates are noisy. In particular, we're interested in 2-qubit gates. So imagine that this U is a noisy 2-qubit gate. So it means that it has some noise channel associated to it. We want to change the noise channel that is associated to a gate to a Pauli channel. To do this, we're going to do something similar, but now we take our gate and we see that it can be, so this is the gate without noise, just theoretically, we take the gate, and we know that this gate can be invariant when sandwiching it between different Paulis. So for example, if we take this C naught, we can sandwich it between Z and Z, but also between X and X in these both sides, etc. All of this is equivalent. Or if we do this same with the ECR gate. So there's many possible combinations, and here we want to take different Paulis to have more different types of combinations, not only 4. In fact, for Clifford gates, we have all possible combinations, which is 16 combinations. And 2-qubit gates in our devices are Clifford in most cases, not when we're implementing fractional gates, but in the rest of the cases, we have that 2-qubit gates are Clifford. So this is, we're going to have 16 possibilities. So now we take our gate and we sandwich it between these two Paulis, but our gate is actually noisy. So we have that our gate has some noise channel associated to it. When doing this, you can see that here you could in principle put these two Paulis. This sums up to the identity. And then we end up with some combination that when we're randomizing over these Paulis, we have that the noise transforms into a noise channel, and this U remains invariant because we chose exactly the combinations that kept the U invariant. So by doing this, this is what we do when we implement Pauli twirling, we end up with noise associated to 2-qubit gates that it's a Pauli channel. So how to implement this using Qiskit? This is pretty straightforward. We just need to define the options as before. We put twirling enable gates equals to true. All these options, you have them in the documentation. So you can find these tables with all the default options and so on. You set enable measure false. We're going to see later what this enable measure means, but this is connected to another error mitigation technique. Twirling dot number of randomizations automatic and shots per randomization automatic. Here you could put a number. So we've seen that there are 16 possible randomizations per 2-qubit gate, but we might have more 2-qubit gates in a given layer. And the shots per randomization is usually because these randomizations are performed within the shots. Imagine that you want to run, so you're computing some expectation value and you want to run your circuit 1,000 times to have a certain precision. If we add some randomizations, these randomizations are going to be performed within these 1,000 times. So you don't have to run the circuit more times, but instead we're just randomizing over that. Then the twirling strategy defines how we're going to twirl, like which 2-qubit gates we're going to twirl and on which qubits we're going to do that. And active accumulated, it's just that we're going to do Pauli twirling on the qubits that have been activated on the circuit so far in each layer. As just a reminder, this Pauli twirling is performed on 2-qubit gates, so the layers of single qubit gates in between are left alone, and we consider that the noise associated to them is independent. This is about Pauli twirling. Then the other technique that has to do with manipulating noise, and in this case learning about it, is the noise learner. What we do with this is that we want to try to characterize the noise that it's affecting the 2-qubit layers in a given circuit. Again, we focus on the 2-qubit gates, not on the single qubit gates, because their noise is larger. So the noise learner needs Pauli twirling because it assumes that our device has a noise that follows a Pauli-Lindblad noise model. And the whole goal of it is to try to learn the parameters of this noise model so that we have some information on how is the device where we're running, that we're using to run our workloads. When you run the noise model, you get these parameters of the noise learner, you get the parameters of the noise model. Problem with the noise learner is that in order to learn these parameters, you're running a lot of different types of calibrations and circuits, modified circuits, and so on. And this means a lot of executions and it adds a lot of overhead, but it can be done in certain cases. So if you wanted to run the noise learner, you need to define, in this case, a noise learner options. And this has a bunch of different things that you can set. So for example, if you run a given circuit with many 2-qubit layers, you can tell it how many of these layers you want to learn. In many cases, let's say, for example, you're doing some evolution, some trotter circuit, it might be that your layers are all the same. So it's enough with just learning 2 of them because then you're just repeating. In some other cases, might be that your circuit is very different, layer to layer, and then it's more complicated. Again, you have randomization, then shots per randomization, because we're performing Pauli twirling. The strategy is the same, and the layer per depth is what is used for the learning of this noise. So you've seen Pauli twirling and noise learner. Now let's see how we undo the effects of noise. So far we've manipulated it, we've learned it, but we haven't done anything to cancel the effects that we're seeing. For this, we're going to see T-Rex, zero noise extrapolation, and probabilistic error cancellation. All of these techniques, these are error mitigation techniques, and they're only valid for expectation values. So whenever we are using the estimator to get the expectation value of an observable, we have a number, and then we can undo the effect of noise on that number. When using the sampler, you have heads of like histograms of probabilities of bit strings. This we cannot use these error mitigation techniques on the sampler. There's error mitigation techniques for the sampler. We've seen M3 before, but in this case, we're going to be focusing on the ones that are implemented in Qiskit. So the first one we're going to look at is T-Rex. T-Rex is an error mitigation technique that is trying to undo the effects of readout errors. So in this case, it has to do with the measurement. So it can happen that, as I was saying before, we have some state prepares, but we're measuring something different. This could be depicted in what it's called the readout error transfer matrix. So we see that, for example, the diagonal would be the case in which we measure the same thing we have, but we could be measuring something a bit different. Like, for example, you see that there's other sides that here that are colored. Imagine that in the axis here, we have some bit strings, for example. So the difference is between the prepared state and the state we would like to measure. It could be, having a 1 and measuring a 0 for each of the different qubits in the device. So that's how I'm like defining the bit strings. In order to detect how we these readout errors happen, we could check, for example, how for each qubit we could prepare state 0 and then see how many times we measure state 0 and 1 from a set of measurements. Or we could prepare state 1 and do the same, and then we would get this kind of calibration matrices per qubit. And we could use this to kind of reproduce the whole, like if we assume that every qubit is independent, which is an assumption, we could do this to reproduce this full matrix. This matrix is 2 to the n to 2 to the n in principle. And then if one could inverse this matrix, it could be used for error mitigation. But this is not efficient in general. So what we would like to have is this matrix to be diagonal, so that then it can be inverted very easily, and the whole thing would become efficient. So we want to change our noise error matrix, let's say, this readout error matrix. Here I'm the transfer matrix, I'm calling it lambda again, to some diagonal transfer matrix. It's similar to what we had before with the gate noise, with the Pauli-Twirling, in which we wanted to change a noise channel to a Pauli noise channel. And we're in fact going to do something very similar to the Pauli-Twirling. Instead of sandwiching our gates between Pauli gates that are different but keep the gate invariant, we're going to sandwich our measurements between Pauli gates, for example, the X, and some change that we do after measuring. We know that the X gate here, what it does, it inverts our, like it does a bit flip. So we could undo the bit flip once we've done the measurement. We're kind of twirling the measurements. We can average, again, over different randomizations, and turns out that by doing this, we end up with a transfer matrix that is diagonal. So then the only thing we need to do is to run these calibration circuits, and we get different values in this diagonal, and then we could mitigate the errors of our observables by dividing by these outputs. So we know that there is some probability that the readout of each of the qubits is going to be a bit different. It's only valid for expectation values because we have to do this thing of dividing the value of the expectation. Like this is just a number. We cannot do this in histograms of parameters, histograms of bit strings, sorry. So now if we want to activate T-Rex, this is actually, again, quite easy with the estimator options in this case. We just need to activate measurement mitigation in this case. This is going to directly activate twirling.enable measure. This has to do with T-Rex. And again, we have a number of randomizations and shots per randomization. I would leave this default in general unless you really know what you want to do with a T-Rex. And then this, by doing all of this, we're enabling this error mitigation technique. The other mitigation technique to undo the effect of noise is ZNE. ZNE is a technique that it's very, so it really has an effect on the results of the estimator again, but it can also be very unstable. So it has good things and bad things, let's say. The idea behind ZNE is pretty simple. Is basically we want to take the noise that we have in our original circuit. So this would be, our original circuit would be this one. We've performed the circuit and it had an expectation value. If we have some way of amplifying the noise on the circuit, we could run the same circuit with amplified noise instances. And then we could do some extrapolation and get the value that we would get of the circuit if the noise level was 0. So we're looking for 0 noise extrapolation point. For the amplification step, we have different options. So there's different ways of amplifying the noise of a circuit we're running on a device. One way is to assume that the noise is proportional to the duration of the pulses. That is how gates are implemented on the circuit. So this is kind of an analog technique, and it would require changing the instructions at the level of the hardware. This is a bit complicated, especially in the way that Qiskit is implemented now, and it's not the most accurate one. So this one is not available right now. But it would be a way of doing it that makes a lot of sense. Just making the gates act for longer times, we have more error associated to those gates. Since gates, right now as they're implemented, they're just always the same duration, we have another option, which is called gate folding. And here what we're going to do, again, this is happening for 2-qubit gates. They're the ones that carry most of the noise of our device. We can multiply our gates several times to increase or to multiply by some noise factor. So imagine you have some unitary gate. If we want to amplify the noise by 3, we can have this unitary gate, its inverse, and again the unitary gate. And this has the same effect. If we want to do it by 5, we can do it 5 times. This is especially powerful when the gate is equal to its inverse, but it can also be done otherwise. And we even have some fractional ways. So we have some ways of implementing fractional noise amplification factors. And in those cases, you could amplify the noise not only by 3 and by 5, but you could do it by 1.2, 1.5, etc. And this is implemented in Qiskit. When we use this fractional noise amplification with gate folding, we're just amplifying the noise of certain gates in the circuit and not others to achieve some fractional factor. This is very nice, but it's limited by circuit depth. So we're increasing the depth of our circuit more and more. And if we have already a very long circuit, doing gate folding might not be very helpful. The other way of doing noise amplification, which can be useful in cases where we have very large circuits, and it actually was implemented in the so-called utility paper, is probabilistic error amplification. In this case, what we want to do is to learn the noise of the circuit, and this is done using the noise learner that I was mentioning before. So we need to implement Pauli drilling to make sure that we have Pauli noise, implement the noise learner to learn what is the noise of our circuit. And once we've learned this noise, we can amplify it in a very targeted way. So we're really amplifying only the noise that we have in the device and not just multiplying the 2-qubit gates. So as I was saying, we implement Pauli drilling. We get the lambda p using noise learning. And then we can do some noise injection using so-called technique with random unitaries. I'm not going to go into detail here, but you could use this to amplify by a certain factor the noise of your device. And in this way, you get these values for the amplification noise factors. Once we've done this, either using gate folding or PA, both are available with Qiskit, then we perform an extrapolation. The extrapolation step is what we do to get the value at zero noise. It's difficult, so this is a very delicate step because it's very difficult to know what kind of extrapolation we want to perform, if we want something linear or exponential. In principle, exponential is going to correct better for the noise because linear, it stays more or less the same scale of noise that we had. And on top of this, we know that when one implements Pauli drilling, we're going to have Pauli noise and the value of expectation values will decay to zero in an exponential way, but we don't really know the scale of this exponential. So exponential is dangerous because it might take us very easily to infinite values. Here's what we see, for example, here. In some cases, all our, for every noise amplification value, we can have expectation values that are close to zero. And then when one tries to do an exponential extrapolation, we just shoot to very, very large values. And polynomial extrapolations in those cases might work better. In Qiskit, what you can do is activate both and see which of the two seems to fit our data better. So if we wanted to enable Z&E, we would define estimator options with a number of shots, optimization and resilience level to zero, as every time that we've shown this. And then we activate the resilient Z&E mitigation. We choose the noise factors. So we have 1, 3, 5 in this case, corresponding to gate folding, but we can have fractional noise factors too, as I was mentioning before. We choose the amplifier. Here we've put gate folding, but we could have PA too. And we can have gate folding front and back depending on how this gate folding is done. But in general, I would advise just choosing gate folding or PA. And we choose the extrapolator. We can have exponential, linear, double exponential, or polynomial. The default is using exponential and linear, checking which of the two is doing a better fit, and then it gives the output for that one. As I said, Z&E in some cases works very well, but it can also be very tricky because choosing this extrapolator is not easy. Finally, I'm just going to mention another mitigation technique, maybe not so much in detail, but PEC, probabilistic error cancellation. is one of the techniques that it has a lot of theory backup. So in principle, it should work very, very well. But then turns out that it's not so easy to implement because it has a large overhead. The idea of PEC is similar to probabilistic error amplification. So in probabilistic error amplification, we want to learn the noise and amplify it. In probabilistic error cancellation, we want to learn the noise and cancel it. So we want to implement an inverse of the noise. The thing is that computing this inverse of the noise is very complicated. It's not, it scales exponentially, and that's why PEC can become very complicated to implement. But basically, it's based on the idea that it's using the idea that you can get the expectation value of some observable with a linear combination of noisy observables. And then if you want to get the right coefficients for all these noisy observables, you must do what I was mentioning before, and this can mean also that you need a large number of shots and so on. So for PEC, you need to activate PEC mitigation, and you can choose a maximum overhead, since the overhead can increase a lot. As I was saying, is a technique that right now it's difficult to implement, but it's very, very promising. Finally, we've been going through the different error mitigation, error suppression techniques, but I also wanted to mention other strategies that are important to address noise. And in particular, I want to talk about validation strategies, and then post-selection and configuration recovery. There's going to be some talks that specifically talk about this, but I think it's important because it's starting to see some techniques for error mitigation that get closer and closer to error correction and bit flip correction. So for validation strategies, the thing is that sometimes what we want to know is that if the output of our quantum circuits, if we're running quantum circuits that run on many different qubits and we don't have a classical counterpart to check that everything is running well. So validation strategies can be very useful when we're running circuits that run on large scales, so large number of qubits, and we don't have a way to check that we're getting results that should be the correct one. So for example, we cannot do the same thing classically. In these cases, we can think about like changing a bit our circuits to obtain something that can be computed classically, then check if the result that we obtain in this case is similar to the classical one, and this can give us an idea on how accurate the results are, and then assume or try to make sure that when we're varying these circuits a bit, we're not changing the noise and the propagation of the noise too much. So on one hand, we can use Clifford circuits for this. Clifford circuits are circuits that are composed with a set of gates that are in the Clifford group. These are the ones that are shown in the slide, are the gates in the Clifford group. And any circuit composed with these gates can be computed classically because there's just a set of rules that you can use that take the initial state that you have to the final state after implementing those gates, and this is an efficient procedure. When one introduces rotations and other types of gates, then we're in the non-Clifford circuit group, and then things cannot be computed classically, which is good because it's exactly what we want to, like, we want to run circuits that are not classically simulable. But what we can do for our circuits is to Cliffordize them, so we change the gates a bit. And then we can check if the Cliffordized version of the circuit is giving the output that it's expected. And this gives us some hint on whether our non-Clifford circuit is working well or not. Another option to do this are mirror circuits. So this is a similar idea. We want to vary our circuit, change it a bit so that we know the output and we can compare it and see if it's giving us what we would expect. In this case, what we do is to implement our circuit and then its inverse. So in this way, if we're starting with a 000 state, we end up with a 0 state. And then we measure and we expect to have the perfect 0000 state. Of course, there will be errors. The propagation of errors will hopefully be similar to the circuit that we had at the beginning, so just U, that will affect this state. So by measuring at the end, we can know how, as we increase, for example, the number of layers, our results get worse and worse. So these two techniques allow us to understand a bit better how errors propagate and how they change by comparing with a known, trivially known result. Yeah. And finally, I want to discuss a bit post-selection and configuration recovery. So as I said, there's going to be a talk that goes into with this to more depth. But in some cases, and this is using the sampler, we can try to detect for bit flip errors and correct them so that they don't have such a big impact on, for example, the expectation value that we're trying to compute. Let's imagine, for example, that we have some preparation of a quantum state and we're measuring sets of samples, bit strings here. Our bit strings would look with like the ones here with zeros and ones. And in some cases, we know that the state that we have prepared must fulfill certain symmetries. This can be, for example, in quantum chemistry Hamiltonians, we have a number of electrons that is conserved. So the number of ones in our bit string should be a specific number. Like, for example, if we have 2 electrons, we're going to have 2 ones. Noise will alter all these bit strings, and some of them will be measured and will have noise and will have errors. So then by knowing these symmetries, we can correct them before reconstructing the expectation value. This is called configuration recovery. Configuration recovery goes a bit beyond this, so it corrects these bit flips by using some iteration and so on. But the main idea is that we want to either get rid of the bit strings that are not correct, or recover the good configurations with configuration recovery in this case. So let's imagine that we're sampling bit strings and we have these ones here, and that we have for our problem n equals 2, so the bit strings must conserve the symmetry of having 2 ones, which that this one is not in the right symmetry sector. So we can perform a bit flip of any of the other bits in order to move it back to the right symmetry sector. Now the question is which of these we should accept, like how do we choose how we perform the correction? Well, in configuration recovery, this is done by using some probability distribution that depends on the problem, on the other bit strings that we've measured before, and this tells us which is the bit that has the most the largest probability to be flipped in order to get us closer to the state that we're looking for. In this case, it would be the first one. So instead of sampling 1000, we sample 1100, and then we've corrected for this bit flip. This is the configuration recovery. For post-selection, in some cases, we just take the bit strings that don't have the right symmetry and we discard them. But what can happen in these cases is that we're left with very few bit strings. It can be implemented in many different ways for many different symmetries. And it's a very promising way of correcting for this type of errors. So as a summary, we've seen that quantum devices have different types of noise. We've had environmental noise, gate errors, spam and readout errors. And then we have different techniques to target each type of noise differently. We have error mitigation that undoes the effect of noise somehow. We have error suppression that tries to suppress some types of noise or modify them. We've seen that there's some validation strategies that can be interesting for certain cases, such as mirror circuits and Clifford circuits. We've seen that for some types of noise like that create errors like bit flip errors, we have things like post-selection and configuration recovery and so on. So the combination of all of these techniques and knowing when to implement which one can really be the difference between being able to run some algorithm and have reliable results or not. On top of all of this, I think using benchmarking and calibration to know how our devices work and then run circuits in the best possible way, this is also super, super relevant, and you're going to see some sessions discussing this. So with this, I would like to end this session, and if you have any questions, we'll be available during the Qiskit Global Summer School. Thank you.